This is a video on 3.6 variation. All right, so let us talk about, there's basically two main types of variation we're going to talk about. One is direct variation and the other is inverse variation. And direct variation, think about like a direct relationship. It means that as when one variable goes up, so does the other. Whereas inverse relationship means when one variable goes up, the other goes down. So there's going to be a couple ways we can tackle this. So let's talk about the first type, a direct variation. And if we look at this yellow box here, if y varies directly as x, then we could say that y equals kx, where k is our constant of proportionality for that particular instance. So in a given relationship, we could always find that constant. So that's going to be method one. So let's do this example. If y varies directly as x, okay, so if that's the case, we know this is the relationship, y equals kx. And y equals 9 when x is 30. Okay, so y is 9 when x is 30. This will allow us to find k. So in this case, k will be 9 over 30. Or if I reduce that, I get 3/10. And once I find k, I can use it to find information about for the second part of this, which says find y when x is 40. Okay, so we know that k is 3/10. So for another value of x, in this case 40, I can use that k to find what y is. So in this case, y will end up being 12. So that's first method. You actually find that constant that defines the relationship between the two variables, and then you use that constant to find the missing variable when you know a different value of x in this case. The second method is, okay, if we're talking about a particular relationship, k is going to be constant for all values in that relationship. So if I know that y equals kx, I can say that k equals y over x. And then I can set up a proportion, because again, in this given situation, k will be the same. So I can say y1 over x1 equals y2 over x2. So setting up that proportion. All right, so let's do this. So the first y was 9, and I knew that when y is 9, x was 30. So I want to find what y is when x is 40. And people probably are used to doing something like this. So I get 40 times 9 equals 30y, and divide by 30. And you're going to see I'm doing it like this because the zeros, I'm just reducing before I multiply. Zeros go away. 3 goes into 9 3 times, so I get y is 12. Yeah, we should get the same thing as before. Okay, so you really can pick which one you feel comfortable with doing. So try the second one, doing the same type of reasoning. Either it's going to be, again, a direct relationship, and you can either use method 1 or method 2. Let's talk about now if they're inversely related. So as one goes up, the other goes down. And the problem would have to specify this, that these are inversely related. And so instead of having y equals kx, notice we have y equals k over x. All right, so method 1 is, let's solve for k first, the constant for this given situation, and then we can find our missing piece of information. So if y varies inversely as x, so I know y equals k over x, and I'm telling you that when y is 20, x is a fourth. So in this case, k will end up being 5. And so then I can use that when I answer the second part. It says find y when x is 15. So I'm going to put in my k, which is 5. So y would be 1/3. Well, what if I like in example 1, wanted to do the second method where I kind of set up, and when I'm not solving for k, well, if that's the case, let's go back to the relationship between k and yk and x. So in this case, if I solve for k in general, it equals y times x. So now what I can set up, instead of doing y over x and y over x, I do y1 x1 equals y2 x2. Because they would have the same k's if you're in the same problem here. So let's solve for it this way. So y is 20 when x is a fourth. Find y when x is 15. So I'm going to get 5 equals 15 y2. So y2 is 1/3. So again, doing the same thing, just different method. Okay. Now let's talk about, and then so you can try the next example. Let's talk about what's called combined variation or higher powers, because it's not just going to be one thing, just talking about how one thing varies affecting another. Often we're doing multiple variables are affecting something. So as it states here, sometimes quantities vary directly or indirectly. Indirectly is the same as inversely. But sometimes they vary that with more than one quantity. And when that happens, oftentimes we'll either say varies directly with these things, or we might say varies jointly, which means directly with more than one thing. So let's do a problem about BMI, body mass index. So it's saying it's directly proportional to his or her weight in pounds and inversely proportional to the square of his or her height in inches. Okay, so let's translate that to words. To an equation. So let's translate those words to words. So it's saying that BMI equals, so we always put our K, and directly proportional, so that's going to go up in the numerator, so directly proportional to weight in pounds, and inversely proportional, so that's going to go in our denominator, to the square of height in inches, so height squared. So really, when you read these problems, read them carefully and maybe underline the important words. Okay, so if that's the case, I'm going to choose to do method 2. So once I have the relationships between the variables down, I solve for k. So if I solve for k here, it's going to equal BMI h squared times h squared over W. So that's going to be k. So I can set each situation equal to each other. So for the first, I know that BMI for this 6-foot-tall person is 24. So remember, height's in inches. So 6-foot-tall is 72 inches, and that's going to be squared, divided by this person weighs 177 pounds, equals BMI for the second, which that's what I'm trying to find. The height of the second is 66, I'm going to square that, divided by a weight of 130. And so you would cross multiply here. So you're going to be doing 130 on your calculator, by the way, 2472 squared equals BMI times 66 squared times 177. So then when you divide, after you multiply the left side and divide by that right side, you should get the BMI to be about 21 if we round it to the nearest whole number. Okay, let's do example 6. Yeah, the force of the wind blowing on a vertical surface varies jointly. Remember, jointly means directly with more than one thing, as the area of the surface and the square of the velocity. So area of surface and square is important to think about. So the force varies directly. So I'm going to put my K, and directly means there's nothing in a denominator in this case. So the area of the surface and the velocity squared. So like before, I'm going to use method 2. So I'm going to solve for K. And let's plug in for the first situation. If a wind of 40 miles per hour exerts a force, okay, so the force is 50 pounds. The surface area is a half. and the velocity of the wind was 40 miles per hour, equals, it's how much force, so force is the missing on the second bit of information, will a wind of 80 miles per hour place on a surface of 2 square feet. Okay, so that's what you're doing. You're going to solve for F, and it should be 800 pounds. All right, so let's do one, because one was hard, and then some of these are tricky. All right, let's undo that. Okay, so Kepler's third law of planetary motion states that the square of the time required, so the square of the time required for a planet to make one revolution about the sun varies directly. Okay, so the square of the time required varies directly, so going not in the denominator, as the cube of the average distance, so distance cubed, from the sun. Okay, so that's the relationship here. And it says, if you assume that Mars is 1.5 times further from the sun than Earth is from the sun, find the approximate length of a Martian year. Okay, so not much information given here, but let's solve for K. So K in this case would be equal to T squared over D cubed. Okay, so let's say time on Earth squared over distance Earth cubed equals time on Mars squared over distance Mars cubed. But remember, Mars is 1.5 times further from the sun than Earth. So and I can replace distance Mars with 1.5 distance Earth. Okay, so let's do that. So 1.5 distance Earth cubed. All right, so if we cross multiply here, I'm going to get 1.5. I'm going to break up the 1.5 and the DE cubed. So I'm going to get 1.5 cubed, distance Earth cubed, times time Earth squared equals time Mars squared times distance Earth cubed. And notice both sides have distance Earth cubed, so those are going to cancel each other out. So now the only thing we can compare time on Mars to is honestly the only time we know is Earth years. So I'm going to compare it to Earth years. So time on Mars, if I isolate that, that just means I'm taking the square root of 1.5 cubed TE squared. Or in other words, time on Mars is going to be equal to the square root of 1.5 cubed times time on Earth. And when we do that, we realize that, okay, so the square root of 1.5 cubed ends up being about 1.837. So time on Mars is 1.837 times Earth years. So that was very variable heavy. I didn't give you a lot of information there. So that one was harder.